let us go ahead and talk about, yeah, there's lots of things to talk about, right? We should probably talk about like all the derivative rules today. So let's start at the beginning. Let's do a few limit definitions and then we'll kind of move along. So what if I wanted to use the definition of the derivative to find f prime of x for the function f of x equal to x cubed. So I would start off I'm sorry, my penmanship, I'll try to use the definition of the derivative to find f prime of x or f of x equal to x cubed. So here's where you should start. And I left off intentionally the word limit. If they say definition, they mean the limit definition. There isn't really any other definition of the derivative that we are aware of here. So we're going to start by just writing, we're going to find that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And I do like writing that part. You can skip that stuff if you really want to and just write out what the actual function is. I like writing that down. I think it's helpful. I drink my water. Okay. Anyway, so then we're actually going to substitute in the actual function. So if f of x is x cubed, then f of x plus h is going to be x plus h cubed minus x cubed all over h. It's probably worth your while to know how to multiply this out without having to like actually do the work, which is kind of memorize it. But I'll tell you there's a trick, which I don't know if Dr. Dill talked about, but we're going to use this for the next one as well, so I might as well point it out. So there's a trick here, and it uses something called Pascal's triangle, which looks like this. You start with a 1, and a couple more 1s, and then the outsides keep having 1s, and the insides you get by adding those numbers together. So 1 plus 1 is 2, you get a 1 over there, you get a 1, 1 plus 2 is 3, 2 plus 1 is 3, 1, and so on and so on. It's a really interesting triangle. It has lots and lots of really interesting patterns in it. But one of the patterns that's there is that these numbers are the coefficients of the binomial expansion. What I mean by that is if you were to write out, say, this one's going to be kind of, so in this 0th row, I would point out that x plus h to the 0th power, well, anything to the 0th power is just 1. But in this first row here, x plus h to the first, I'm going to be a little bit annoying about it. It's 1x plus 1h. And in the second row here, x plus h squared is 1x squared plus 2x to the first h to the first plus 1h squared. And notably, those numbers that are the coefficients are just the numbers that are in Pascal's triangle. So it shouldn't be a surprise that in this third row, we're going to get that x plus h cubed is going to be 1 times x cubed plus 3 times x squared times h to the first plus 3 times x times h squared plus 1 times h cubed. And that pattern persists, meaning these are the coefficients and the powers, you always start off with like x to the highest power, and then the power of x just decreases by 1, and the power of h just increases by 1. So I want you all to take a quick second and write out the expansion for x plus h to the 4th. I'll give you like 30 seconds. I got my water. So using this 4th row of Pascal's triangle here, and you know which number row it is by just whatever the second entry in the row is. So if the 4 is the second entry, that's the 4th row. If the 5 is the second entry, that's the 5th row. So in my 4th row here, my coefficients are 1, 4, 6, 4, 1. So I'm going to get 1x to the 4th plus 4x to the 1 less power, h to the 1 more power, plus 6x to the 1 less power, h to the 1 more power, plus 4x to the 1 less power, h to the 1 more power, plus, squeeze it in, h to the 4th. So that's useful to us when we try to then deal with using the limit definition of the derivative to find the derivative of x to the third. Because then we can just say, oh, I don't need to do x plus h times x plus h times x plus h. I just know that x plus h cubed is going to be x cubed plus 3x squared h plus 3xh squared plus h cubed. So we're going to write this as the limit as h goes to 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all divided by h. Here's what should happen with these problems every time you're doing a limit definition of the derivative. After some work, and there might be more work than what we've just done, but after some amount of work, you should be able to cancel every term in the numerator that does not have an h. In this case, it happens right away. X cubed minus x cubed is 0. Every remaining term should have an h, but you can then factor out. So if I factor out an h to the first, I'm left with a 3x squared. I'm left with a 3xh plus h squared, all divided by h. And then h divided by h is 1. So I'm left with the limit as h goes to 0 of 3x squared plus 3xh plus h squared. And now that we've dealt with the problematic h that was in the denominator, it's not there anymore. We dealt with it. The rest of the h's we can let go to 0, meaning we can take the limit as h goes to 0 and just plug in 0 for each of the remaining h's. You get 3x squared plus 3x times 0 plus 0 squared. You really don't need to write that. You can just say it's 3x squared. That is the derivative of x cubed. A couple more of these, and then we'll talk about the general rule. Sorry, I was kind of gross. Apologies. Let's do the same thing for x to the fourth, which is one of the reasons we did that for Pascal's triangle, so that we can have the next one. So let's do the same thing. If our function is x to the fourth, let's use the limit definition to find the derivative. And again, if you're me, I know you're not, but if you were, you would write it as just limit as h goes to 0 of f of x plus h minus f of x all over h. I like writing this down. It lets the person who's grading my work know that I know what the limit definition of the derivative is. Even if I screw up the next part, at least they know I knew what the definition was. So then we write this as the limit h goes to 0 of, well, our function is x to the fourth. If it helps, you can write down right next to it that f of something else is something else to the fourth. In this case, the something else is x plus h. That's going to be the limit as h goes to 0 of x plus h to the fourth minus x to the fourth all over h. We do the same thing. We expand out x plus h to the fourth using Pascal's triangle that we just talked about. I know it disappeared. Oh yeah, sorry, it's back there. So it's going to be the limit as h goes to 0, and x plus h to the fourth is going to be x to the fourth plus 4x to the third h to the first plus 6x squared h squared plus 4x to the first h cubed plus h to the fourth minus x to the fourth, all divided by h. And the same kind of thing that happened before happens this time as well. X to the fourth minus x to the fourth is 0. You could even, if you want to, kind of skip a step and say, if we divide everything else by h, we're going to get the limit as h goes to 0 of, let's see, 4x cubed h divided by h is 4x cubed. 6x squared h squared divided by h is 6x squared h to the first. 4xh cubed divided by h is 4xh squared. Essentially, each term has one less power of h, and h to the fourth divided by h is h cubed. And then we can plug in zeros for the remaining things that have h's, so you get a 0 there, a 0 there, and a 0 there. So not surprisingly, we end up getting 4x cubed. Which leads us to an idea of the general pattern for taking the derivative of x to some power. It looks like in both these cases, for x to the third, we had that third power times x to the 1 less power. Same deal here. For x to the fourth derivative was that fourth power times x to the 1 less power. And that is the idea for what we call the power rule. So what if f of x was equal to x to the n? N, P, I don't care. I like to use N. I'm too like, no, let me use P actually just because my N's and my H's sometimes look a little too similar. Let's say we have X to the P, just to make it less terrible. So we want to find f prime of X. And once again, it's going to be the limit as H goes to 0 of f of X plus H minus f of X all over H, which is going to be the limit as H goes to 0 of X plus H to the P minus X to the P all over H. And now we have to figure out what X plus H to the P is. And the problem is, it's kind of a pain to write it all out. If we go back to our Pascal's triangle for a moment. So I just want to, so I'll cover this up here. Okay, yeah, sure. Sorry, kind of all over the place. Not great, James. Oh well, such is life. It will be not great for a second. Sorry, we'll come back to it. So I want to point out that when I had X plus H to the 4th, I got X to the 4th plus 4 times X to the 1 less power, H to the 1 more power. And that's always going to be the pattern. So when it, like for here, if I was doing X plus H to the 5th, it would be 1 times X to the 5th plus 5 times X to the 4th times H to the 1st plus other terms. And I could write them down, right? It's 10x cubed H squared plus 10x squared H cubed plus 5x H to the 4th plus 1 H to the 5th. But the point I'm really trying to emphasize here is that this power is always going to match that coefficient. In each of these, right? This power matches that coefficient, this power matches that coefficient, and so on and so on and so on. So we can accurately, confidently guess that if you have x plus h to the pth power, you're going to get 1 times x to the p plus p times x to the 1 less power times h to the 1. And then you're going to get a bunch of other things. I don't actually, well, there's not a nice way of writing out the rest of the terms without getting too deep into how the math works for that particular thing. It's not that important. So I'm just going to say, I know I'm going to have some constant times x to the 1 less power times h to the 1 more power. And then it just goes on and on and on. The powers of x getting 1 less, the powers of h getting 1 more each term, until we get to the couple last terms where the second to last term is going to be p times x to the 1st times h to the p minus 1. And we know it's a p because there is symmetry, right? I have a 5 here just like I have a 5 here. I have a 4 here just like I have a 4 here. And then finally, the very last term would be 1 times h to the pth power. Are there questions about what I've written? So all we're saying is that we multiply out x plus h to the p power, you get 1 times x to the p plus p times x to the p minus 1 times h plus something times x to the p minus 2 times h squared plus something times x to the p minus 3 times h cubed, and so on and so on and so on, all the way to the very end, you're getting p times x times h to the p minus 1 plus h to the p. And then we're going to go back to our limit definition of the derivative and say, okay, well, great. We're going to plug that all in for x plus h to the p right here, and then we're going to subtract x to the p off it. So here's what we get. We get a big old mess. We get the limit as h goes to 0 of x to the p plus p times x to the p minus 1 times h plus some constant times x to the p minus 2 times h squared plus a bunch of other terms until the very, very last couple terms, p times x times h to the p minus 1 plus h to the p all over h. Oh, sorry, I forgot something. I forgot the minus x to the p. That's super important. We need that. And just like in the previous two examples, the same thing is going to happen. We're going to cancel or subtract the x to the p minus the x to the p. That's going to be 0. And then every other term that's left in the numerator has at least an h to the 1st. So if we divide each thing in the numerator by h, well, look what happens. If the limit of h goes to 0, p times x to the p minus 1 times h divided by h, well, those h's cancel, and you get p times x to the p minus 1. This next term, this constant times x to the p minus 2 times h squared divided by h, well, h squared divided by h is h to the 1st. So you get c2 times x to the p minus 2 times h to the 1st. And then every other term in between that I didn't write is going to have a higher power of h, right? Each of these next terms is like h cubed, h to the fourth, et cetera, et cetera, et cetera. And when you divide by an h, there's still going to be some higher power of h left over. So up until the very, very last couple terms, where this term here, p times x times h to the p minus 1, if you divide that by h, you're going to get p times x times h to the p minus 2, because the power of h is going to be 1 less than it was before. And lastly, h to the p divided by h is going to be h to the p minus 1. Again, when you divide h to a power divided by h to the first, you're just really subtracting those powers. And then, just like before, all of the h's get to go to 0. So this term goes to 0, these middle terms go to 0, this term goes to 0, that term goes to 0, and you just end up getting p times x to the p minus 1. Which is the rule we were alluding to in the first place, right? That you take the derivative of x to a power, it's that power multiplied by x to the power minus 1, or 1 less. This is your general power rule. And even though we've kind of technically only shown that it's true for powers of p that are positive integers, right? Because this expansion only really works if the power is like 3 or 4 or 5 or 6 or some nice positive integer. It works for any power that's a real number. So whether it's positive, whether it's negative, whether it's a whole number, whether it's a fraction, whether it's irrational, any number works. So it's certainly true that we can say that the derivative of x to any power is equal to that power times x to the new power minus 1, or the old power minus 1. And this is called the power rule. And it's true for any power. So for example, I should say, yeah, the power rule, and this is true for any number p. So for example, if I want to find the derivative of x to the negative third, I'm just going to use the power rule. Say, well, the derivative is going to be, take my power, and it's going to be that power multiplied by x to the, and then I'm going to do my old power minus 1. So it's going to be the power of negative 3 minus 1. That's going to be negative 3 times x to the negative fourth. Or if you've had something weird like, I don't know, the derivative of x to the pi squared. Pi squared is just a number. It's not a nice number, but it is just a number. It's probably between 9 and 10. And whatever that is, my derivative is going to be that number multiplied by x to the 1 less power. Not ideal, but that is the right way to write the answer to this question. I know. So then we kind of start doing some new things. Like, for example, let's say we have the function f of x equal to x to the 10th plus the cube root of x squared plus 1 over x to the 5th plus 7. We want to take the derivative. Good rule of thumb is that whenever you're taking a derivative, before you take the derivative, it's usually going to be in your best interest to simplify the expression as much as possible. Specifically here, I would much rather rewrite this as x to the 10 plus, instead of writing the cube root of x squared, I would much rather write that as x to the 2/3 power. Same deal here. I want to point out the derivative of 1 over x to the 5th is not 1 over 5x to the 4th. We have to rewrite this as x to a power not in the denominator, and then we can use the power rule to take the derivative. So we're going to rewrite this as x to the negative 5th plus 7. And now we are ready to take the derivative. So our derivative is going to be 10 times x to the 9th plus 2/3 times. Okay, here's a situation where you can do one of two things. You can either just do the subtraction, but if you're not that great at subtracting fractions, it's fine to write 2/3 minus 1. It's correct, right? We know that the new power should be 1 less than the old power. Cool. Then for this one, we're going to get, I don't want to write plus -5, although you can. I'd rather just write -5 times x to the negative 6. be careful there. In case people subtract the wrong direction because they're like, oh, it should get less, but less is more negative when it's already negative. And then finally, what's the derivative of 7? 0. Because constant functions, one way to think about the derivative is the slope of the line or the slope of the tangent line. And for constant functions, the slope is always 0, so the derivative is always 0. And then I would feel compelled to simplify this and actually do the subtraction here. So I do think you should at least write this as 10x to the 9th plus 2/3 x to the negative 1/3. I think you can leave negative 5x to the negative 6 as is. In fact, I would leave it as is if I was going to take more derivatives because it's already written the way I would want it to be written as. Let's look at one more example of this before we do some other things. Yeah, this section, well, this I'm looking specifically at section 3.3. 3.3 like feels like it has like a million things in it. Like there's the power rule, and then the trig derivatives, and the derivative e to the x. Like it's just like a lot of stuff. So we'll get there though. Or I should say derivative of sine and cosine. Let's look at a couple more examples. Let's say we had this one. F of x equal to 4x to the 7th plus 3 over the square root of x plus 5x plus e to the 3rd. And again, before we start doing any differentiation, we should, I should maybe say like find f prime of x. I should maybe say instructions here. Before we do that, we should simplify. I want to be extra explicit here. When we simplify this, we shouldn't write f prime of x, right? We're not finding the derivative yet. So if you're just simplifying, you really should be only simplifying or only differentiating. You shouldn't be like mixing it up. If we're just simplifying, we should write f of x. And it's equal to 4x to the 7th plus this 3 divided by the square root of x is 3 times x to the negative 1/2. And then everything else is good. 5x is fine. E cubed is fine. Now we're ready to differentiate. So the derivative of 4x to the 7th is going to be 28x to the 6th. Right? The 4 times 7 is 28, and the power is 1 less. Same deal here. 3 times negative 1/2 is minus 3/2 times x to the negative 1/2 minus 1 is negative 3/2. The derivative of 5x, so you could think of it if you wanted to as 5x to the 1st, and the derivative is 5 times 1 times x to the 0. But really, I would encourage you to think of it as, oh, that's just like the line y equals 5x. And the derivative of that, well, the slope of the line y equals 5x is just 5 all the time. So the derivative of 5x is always 5. So for straight lines, the derivative is just the slope, whether the slope is 0 if it's horizontal or 5 if the slope is 5. And finally, the derivative of e cubed is 0. The trick. I'm trying to trick you there. Someone's trying to trick you there when they write. So if you look at this here, here's the question you should ask yourself. Do you see a variable? What's our variable for this problem? X. Do you see an X there? No, we don't. If you don't see an X or whatever your variable happens to be, it's a constant. It's maybe not the nicest constant ever, but it is just something that is never changing. If you plug in e cubed to your calculator, it's going to spit out a number, and it's always that number. So that's a constant, and constants have a derivative that is always going to be 0. So don't get tricked, right? Someone might write like pi squared or pi to the 5th or e to the 17th. All those are constants. Don't get fooled. And then we should leave it like that. So, and I wouldn't write the plus 0 normally, but it's fine right here. Couple rules I want to point out that we're using without even thinking about using them. We are using the constant multiple rule, which is where if you have a constant times a function, you just take the derivative of the function and multiply the constant by that. So really, when we took the derivative of 4x to the 7th, the rule we were using without even thinking about it was the fact that this is equal to 4 times the derivative of x to the 7th, which is, sorry, that's right, yeah, which is 4 times 7x to the 6th, which is 28x to the 6th. You shouldn't think about using the constant multiple rule most of the time. Most of the time, it's just going to happen naturally. Like, oh yeah, we took the derivative and multiplied the numbers together. The other rule that we also used without even thinking about it was the addition and subtraction rule, right? When you take the derivative of a bunch of things added together, you just take the derivatives of each piece and add or subtract the results together. So again, we're using these rules, and I guess I can write them down, right? The constant multiple rule says you want like official rules that the derivative of a constant times a function is equal to the constant times the derivative of the function. And the sum or difference rule says that if you take the derivative of the sum of f of x plus g of x, it's just going to equal the derivative of f of x plus the derivative of g of x. And it's true whether you're adding or subtracting. But again, you shouldn't really be thinking about these rules. They're just going to happen naturally. You're just going to be like, oh yeah, we took the derivative of this piece, added the derivative of the next piece, added the derivative of the next piece, and then we were done. Yeah. So yeah, we should do that. Okay. And we should talk about a couple more things here. Let's look at two more examples here. So here's an example. I want to find the derivative of f of x equal to, all right, 1 second, x squared plus 3x times x to the 4th plus 2. Oops, you can't quite see that. And while you might have already learned the product rule, I wouldn't use it here even if I knew it, because this one is so easy to multiply out, we should just multiply it out. So if you can multiply something out, it's often easier to take the derivative that way. So if we multiply this out, so again, we're still writing f of x as we're not actually differentiating yet. We're just going to multiply this out. X squared times x to the 4th is x to the 6th. X squared times 2 is 2x squared. 3x times x to the 4th is 3x to the 5th. 3x times 2 is 6x. I don't really care that I've written this thing out of order, right, in the unstandard form, but we could rewrite it if we wanted to, if we need to. And then the derivative is a straight shot. Derivative of x to the 6th is 6x to the 5th. Derivative of 2x squared is 2 times 2x, which is 4x. Derivative of 3x to the 5th is 3 times 5, so 15x to the 4th. And the derivative of 6x is just 6. So I'm going to bang on this drum a little bit more. It is almost always correct to simplify a function before taking its derivative. I will also say that if you're taking a second derivative, it's usually a good idea to simplify your first derivative before taking your second derivative. Let's look at one more example before we talk about some other rules. So if our function was, say, 2x to the 4th plus the square root of x plus x to the 9th divided by x cubed. Yeah, that's fine, sure, x cubed. I want to take the derivative of that. And again, even if we knew the quotient rule, I still wouldn't use it here, because this is easier to deal with if we just simplify by divide, specifically because our denominator has only one term. So since if your denominator has only one term and it's like x to a power, you can typically just divide everything by that one term. So it would definitely be in our interest to write this as 2x to the 4th divided by x cubed, plus I'm going to rewrite this as x to the 1/2 divided by x cubed, plus x to the 9th divided by x cubed. Then we're going to simplify it one more step. 2x to the 4th divided by x cubed is 2x. X to the 1/2 divided by x cubed, we're subtracting those powers, and 1/2 minus 3 is 1/2 minus 6/2, which is -5/2. And then x to the 9th divided by x to the 3rd is x to the 9 minus 3, which is x to the 6th. And now we're finally ready to take the derivative. So the derivative of 2x is 2. The derivative of x to the -5/2 is -5/2. X to the -5/2 minus 1 is -7/2. And we're going to get plus 6x to the 5th. So yes, again, if you can simplify before differentiating, it is usually a good idea to do so. There's a couple other functions in this section that we should talk about taking the derivative of. And again, I'm specifically referring to section 3.3. So yeah, there's 3 functions I can think of that we need to talk about. And they are sine, cosine, and e to the x. So there is a long way of finding the derivative of sine using the limit definition, which you might have already seen, which I don't know if you really need to see again or really at all, but you need to know what the derivative of sine is. So here's how I would encourage you to think about the derivative of sine. Let's graph it. So we're going to graph f of x equal to sine of x. Trying to do a nice job. We're going to graph one period from 0 to 2 pi. We're going to break that up into 4 equal quarters like we usually do. So that's pi over 2, pi, 3 pi over 2. Let me zoom in a little bit so I can see what I'm writing maybe a little bit better. And then sine has a range from -1 to 1, with the low of -1, high of 1. Starts in the middle, and then goes up to 1, and then back down to 0, and then down to -1, and then back to 0. It looks like this. It's your typical sinusoidal curve. I will point out that sine and cosine are pretty much the same function. They're just like shifts of each other. Okay, so here's how we're going to graph the derivative. This is actually a good skill to have for any kind of a graphing kind of thing. But to graph the derivative, we're just going to look at the slopes of the tangent lines. So let's try and make our lives easy here. We're going to draw this right below. I want to use blue, all right? Try to line things up here. Okay, so I'm going to get the same point here. Here's what we're going to do. I'm actually going to pick the easiest points first. So I'm going to point out that at pi over 2, my tangent line is horizontal, meaning the slope is 0, meaning the derivative is 0. So if I'm trying to graph the derivative, I know that the value should be 0 when x is pi over 2. So graphing the derivative, I should have this point right here. When x is pi over 2, the derivative is 0. Where else between 0 and 2 pi is the derivative also equal to 0? Yeah. Is that what you're going to say too? Yeah. Yeah, right there, the slope is also 0. So right here, the derivative has a value of 0. Between 0 and pi over 2, the slope is definitely positive. Right? Slope, if I drew a tangent line there, it'd be a positive slope, positive slope, positive slope. If the function's increasing, it has a positive derivative. What I specifically want to point out, though, is right at the origin, if you've drawn this well, your tangent line slope looks like it has a slope of about 1, because it does. And I've drawn that slightly poorly. Oh, well. I'll tell you why in a second. Similarly, over here at pi, tangent line has a slope of -1. The reason I said I've drawn this slightly poorly is because technically these points are extra special. They're also inflection points, which we'll talk about later in the quarter. But the tangent line should actually go through the function, when I didn't draw it so nicely over here. So don't worry too much about it, but I just don't want to mislead you. So over here at pi, the slope of the tangent line should be -1. And finally, back at 2 pi, well, we've done one full cycle. So we've gotten back to 2 pi. We should be doing the same thing that we're doing over at 0, which is having a slope of +1. And if we graph these points, hey, that function looks familiar. As long as I don't graph it poorly. What does that look like? It looks like cosine. It is cosine. So if your function is sine of x, and this is the graph of your derivative, it's exactly cosine of x. And if you really wanted to, you could apply the same sort of logic to find the derivative of cosine. You could, again, draw the graph of the derivative and say, okay, well, I'll do this one a little bit quicker here. So at 0, the slope of the tangent line is 0. At pi over 2, the slope of the tangent line is -1. At pi, the slope of the tangent line would be 0. At 3 pi over 2, the slope of the tangent line would be +1. And finally, at 2 pi, the slope of the tangent line would again be 0. So this looks like, I should zoom back out. I was like, why can't you see the whole thing? This looks like I took the sine function and did what to it? Flipped it over, which means I put a negative out in front of the sine function if I gave it a horizontal flip, sorry, a vertical flip, apologies. So it definitely looks like the derivative of cosine is in fact negative sine of x. And that is also true. So this lovely cyclical pattern for sine and cosine, where you just cycle through all the derivatives. So if your function is sine, the derivative of that is cosine of x. The derivative of that is negative sine of x. The derivative of that is negative cosine of x. I'm really just using the constant multiple rule there and saying, oh, if the derivative of sine is cosine, then the derivative of -1 times sine is -1 times cosine. And then finally, if you take the fourth derivative, once you get to the fourth derivative, we start writing a little parentheses for instead of writing like prime, 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 prime. The fourth derivative is going to be back to positive sine of x. And then someone can ask you a stupid question like, if f of x equals cosine of x, what's the 97th derivative of your function? And you're like, okay, well, every time I do 4 derivatives, I know I get back to where I started. So what's the biggest multiple of 4 that's less than 97? It's either 96 or 94. Pretty sure it's 96. So if I do 96 derivatives, I'll get back to where I started. So this is, so let's say, this, and I'm going to use different notation here. So I'm going to say that this is the, I hate this. No, I do like this. This is the 97th derivative of cosine of x. And then here's what I'm going to do. I'm going to say that's really 1 derivative and then 96 more derivatives. I know this notation is not everyone's favorite, but it is useful here. Okay, so look what I've done. I've written it as the derivative of 96 derivatives of cosine. But we know that 96 derivatives of cosine gets us right back to cosine. Because if you do 4 derivatives, you get right back to where you started, as long as it's sine or cosine or negative sine or negative cosine. Anything else? No. So then that's the same as just the derivative of cosine, which we can then say, oh, well, the first derivative of cosine is just negative sine of x. So it is true that the 97th derivative of cosine is negative sine of x. Sometimes people like to ask questions like that. Okay, let me see time. So sine and cosine, yeah, we're good there. Definitely should memorize those for sure. Yes. Yeah, I was trying to write it in a way that explicitly kind of showed the work. But yes, you could say, you could write down words of like, oh yes, if I write like 97 divided by 4, you're going to get 24 with a remainder of 1. And then you can say, oh, well, that's the same as just the first derivative. So really, yes, it's whatever your remainder is, that's how many derivatives you actually have to take. Yeah. All right. The other function we should talk about briefly is e to the x, which is kind of a pain. Yeah, I don't know. Yeah, I don't love that we're talking about e to the x right here. Yeah, it's not great. There's only like one thing here. Yeah. Yeah, they just kind of say it, right? They don't even like prove it. No, they really don't. Did your teacher? Oh no, they do kind of. Yeah, wow. Not in love with this part of the book. Okay, so f of x is equal to e to the x. The derivative is also e to the x. Did Dell talk about why this is true? Okay. Did it feel somewhat substantial? Like, did it feel like it made sense? No, okay, fair enough. So let's briefly talk about this. Here, so the thing is, E is kind of a special number. It's actually a really special number. It's the natural base. And you might have seen once upon a time that it's actually defined as a limit. You might not have, but it is true. And I don't love I really don't love that they have written it that way. That's kind of the worst thing I've ever seen personally. But the actual good way of defining E as a limit, or one of the 2 good ways, is we can say that E is the limit as n goes to infinity of 1 plus 1 over n to the nth power. There's an example that people talk about where you kind of talk about like, if I lent you $1 and charged you 100% interest and compounded it continuously, this is what you would get. So how much time have we got? Never enough time. Let me just say though, Here's your compound interest formula. I know it's been a minute. The amount of money you have at time t is your principal times 1 plus your interest rate divided by n to the nt power. This is a reminder. P is the amount of money you're starting with or being lent. R is your interest rate as a decimal. N is the number of times per year you're compounding your interest. And T is the number of years. So here are the details. I'm going to lend you $1. It's a nice guy. Not that nice. I'm going to charge you 100% interest. I'm a loan shark. But really, that's a 1. And then I'm only going to lend it to you for 1 year. So rewriting this, look what we've got. We've got that the amount of money I'm going to have from you, because I'm a loan shark, is going to be $1 times 1 plus 1 over n to the n times 1 power. So the only thing that matters here is how many times per year I compound the interest. So if I only compound it once, at the end of the year, how much are you going to have to pay me? Good question. How much are you going to have to pay me? I lent you $1. I charge you 100% interest. How much do you give me back? Not just $1, not $100. $1 plus 100% of another dollar. $2, right? I get my dollar back that I lent you, plus the 100% interest that I charged you, which is another dollar. So that totally works out. If you plug n equal to 1 into the formula, look what happens. You get 1 plus 1 to the first power, which is 2 to the first, which is 2. So I lent you $1, and I only compounded interest once per year. I would get back $2. Okay, we're going to do 2 more of these, and then we'll talk about the final result here. If I compounded interest twice per year, semi-annually, that means halfway through the year, after 6 months, I charge you half of the interest, so 50%. So after 1 year, I'm going to charge you 50% interest. So that's going to be 50 cents, right? So I lent you $1. Now I have now you owe me $1.50, but now I'm compounding interest. So now I'm going to charge you the rest of the interest on that $1.50. So then at the end of the year, 6 months later, I'm going to charge you the other 50% on that $1.50, which is going to be 50% of $1.50, which is 75 cents. So at the end of the year, you're going to owe me $1.50 plus 75 cents, which is $2.25. Or we can just use the formula. If I plug it in the formula, I get 1 plus 1/2 squared, which is 3/2 squared, which is 9/4, which is 2 1/4. So that's the idea of compound interest, that the more times you compound interest per year, the more money you're going to generate, because you're calculating interest on interest. And now the question arises is, what happens is you let the number of times you compound this become more and more and more during the year. Like if you did this every day, like if I compounded interest 365 times per year, I don't remember what we get because I didn't write it down. We get a number that's close to like I think it's like 2.68 approximately. And if you let this number, if you compound continuously, if you let that number approach infinity, guess what number we get closer and closer to? Yeah, that one. E, approximately 2.71828, et cetera, et cetera, et cetera. So that's the whole idea. That's what E is. And you can certainly define E as the limit of this expression. Sorry, I know that was kind of a long trip to get there, but I think it's worth knowing that that is actually something that's true. Okay, now I'm going to write down this limit in a slightly different but equivalent way. Instead of saying that the limit as n goes to infinity of 1 plus 1 over n to the nth power is equal to E, watch this. Now, I'll just do it this way. I'm going to let h equal 1 over n. Yeah, that's fine. Yeah. So then I'm going to say, if n goes to infinity, what's h going to go to? If n gets really, really big, h equal to 1 over n is going to get really, really small. So we're going to rewrite this limit as the limit as h goes to 0 of 1 plus, well, let's see, 1 over n is h. So I'm going to write 1 over n is h. And this is where I have to be really careful, make sure my n's and my h's look different. 1 over n is h, and n would be 1 over h. And that limit, I didn't really change anything. I just use different letters, but it's still the same thing. The limit should also be e. Okay. Now we're ready to actually maybe feel good about taking this derivative. Maybe not. You might not feel good about it, but at least you'll have seen something that might make some sense. So I'm going to take the derivative of e to the x. And I'm going to do that is by using the limit definition. The limit as h goes to 0 of f of x plus h minus f of x all over h, which is going to be the limit as h approaches 0. Well, f of x plus h is e to the x plus h minus e to the x all over h. And then we're going to simplify this. We're going to break up e to the x plus h as e to the x times e to the h. And then we're going to factor out e to the x. So you get the limit as h goes to 0 of e to the x times e to the h minus 1 all over h. Now this is where it would be nicer if I just used the book's weird definition of e. That e is in fact the limit as h goes to 0 of this expression. E? Oh, sorry, no, that's not true. That's 1. Okay, yeah, I do not love that they do that. So, but what I'm gonna do instead is I'm gonna say, well, look, I know that e is equal to this limit here. So I'm actually going to do something kind of sneaky. I'm going to replace e with all of this. I'm not going to write the limit there, though, because the limit's already there. So I don't need to write the limit twice. It's kind of a shady move, I'm not going to lie, but it's totally fine. So look what happens. I get the limit as h goes to 0 of e to the x times e, which is now this gross mess, 1 plus h to the 1 over h. That's what's going inside the red box there. Then still raised to the h power, minus 1 over h. But now look what happens. 1 plus h to the 1 over h to the h, what happens to those powers? Right, they multiply to 1. Then you have 1 plus h to the 1. 1 plus h minus 1, the 1's cancel. So you get h over h, and h divided by h is 1. So all of this stuff here just goes to 1, and we're left with e to the x times 1, which is e to the x. Kind of tricky, but it does work. Do you need to know this? Really? Probably not. Do you need to be able to reproduce this? Definitely not. But it is good to have seen it. I think so. I wouldn't have showed it to you if I didn't think it was good for you to see it. So, end of the story. Derivative of e to the x is e to the x, which is always kind of nice, but also kind of terrible because you have to remember that when you're taking the derivative of e to the x, you're actually doing a thing and then getting e to the x. All right, let's mosey along here. Oh, I should say one more thing about this. So then we can use the rules we've already got and say, like, what's the derivative of 5e to the x minus sine of x plus 4 cosine of x? And then we can just use our constant multiple rules and our addition and sum rules to say, oh, well, the derivative of 5e to the x, the 5 should hang out. I like to say the constant multiples hang out when you're taking a derivative. So the derivative of 5e to the x is 5 times the derivative of e to the x, which is e to the x, minus the derivative of sine of x is cosine of x, plus 4 hangs out, and the derivative of cosine is negative sine of x. And I would have been smarter about this and written this as minus 4 sine of x, but I forgot that was going to happen, so I didn't. And I guess you could rewrite it as 5e to the x minus cosine of x minus 4 sine of x. So now, with one exception, no, a couple exceptions, we know most of the derivative rules we're going to need to know. The exceptions being the natural log of x and the 4 other. All right. As far as functions, we need to be able to take the derivative of. But there are some rules we need to be able to take some other more complicated derivatives. So here's the issue at hand. I would really like to take the derivative of, say, f of x equal to x cubed times sine of x. And the problem is we don't have a rule for that yet. and I want to make sure it's explicitly clear. Like, I cannot say this enough. The derivative of this is not 3x squared times cosine of x. Not the derivative. Or in other words, we can't take the derivative of two things multiplied together by taking each of the derivatives and multiplying the result together. So what do we need? We need the product rule, the rule for taking derivatives of products. It's not that hard to derive, but I don't think we should spend our time doing that because we only have 30 minutes left and there's so much to say. So I'll tell you that here it is. Here's the product rule. If you want to take the derivative of the product of f of x times g of x, I always think of it as you get the derivative of one piece times the not derivative of the other piece, and then you add and you do it the other way. So it's usually written as f prime of x times g of x plus f of x times g prime of x. Or the derivative of one piece times the other piece plus the not derivative of the first piece times the derivative of the other piece. Or however you want to say it. So to go back to this function here, I want to take the derivative of x cubed times sine of x. It's going to equal 3x squared times not cosine times sine of x plus, and then we switch it. We leave the first one alone, so we leave the x cubed alone, and we multiply by the derivative of sine, which is cosine of x. And that's our full answer, and there's nothing really else we can do with it. Okay, so why don't you all try taking the derivative of g of x equal to x to the sixth times cosine of x. Try finding that derivative. I will say that if it helps you, lots of people like to give each of the pieces that are multiplied together a new name. I wouldn't use g here since I've already used g for the function name. So if I've already used f or g, I usually like to call them u and v, or sometimes I guess f and h, but I don't like that as much. So I would call this u and this v, which I know are terrible choices if your penmanship isn't great because they're letters that look the same. Oh well, it's a common choice for other things in the future. So here, I know I'm going to do the product rule. So it's the derivative of the first thing times the not derivative of the second thing, plus then you switch it. Leave the first thing alone, multiply by the derivative of the second thing. So my u prime here is going to be 6x to the fifth. My v is going to be just cosine of x. We leave it alone. I know it's real tempting to take the derivative there, but we have to leave it alone. Plus, then we switch it. We leave the x to the sixth alone. We multiply by the derivative of cosine, which is negative sine. I do highly recommend if you have the negative there, put parentheses around it. Otherwise, it looks like you have like x to the sixth minus sine of x, which is not the same thing as x to the sixth times negative sine of x. But really, we should have anticipated that and written it as 6x to the fifth cosine of x minus x to the sixth times sine of x. One more product? Yeah, one more product. Sure, why not? What if our function was r of x equal to x to the seventh times sine of x times e to the x? Ooh, a triple product. There's a couple ways to deal with this. One way is just to treat it, so to pick one piece to be its own kind of thing. I know it sounds silly. Here's what I mean. You can say, well, I'm going to think of this as x to the seventh as my f, and sine of x times e to the x as my g. So here's what I'm going to do. I'm just going to apply the product rule. So my R of X, sorry, my R prime of X should be F prime times G plus F, which is X to the 7th, times G prime. Now, here's what I'm going to do. I'm going to not write it out just yet. I'm just going to write it as sine of X times e to the X prime, which means I still have more work to do because there's an unresolved derivative there. But now for sine of X times e to the X, to take the derivative of that, what rule do I have to use? The product rule again. So then we're going to get 7x to the 6th times sine of X times e to the X plus X to the 7th times product rule here. Derivative of sine is cosine of X times leave the e to the X alone. Right, that's an e to the X that I didn't take the derivative of. Plus, then we leave sine of X alone and we take the derivative of e to the X, which is e to the X. And then I don't think we need to distribute here, but I'm going to distribute because I want to show you what the real kind of result here is. So we distribute this X to the 7th to both terms. Look what I get. I get 7x to the 6th times sine of X times e to the X plus X to the 7th times cosine of X times e to the X plus X to the 7th times sine of X times e to the X. Or as I would think of it, you have, if I call these pieces h of X and j of X, I have f prime times h times j plus f times h prime times j plus f times h times j prime. Or as I would say, you have the product of all three pieces where in each piece, one of the pieces' derivative has been taken and the rest of them have not. And you could extend this idea to the product of any number of things. So there is a triple product rule and a quadruple product rule and however many things you want. And I will just point out that you don't need to memorize these, but occasionally it's useful to know that if your regular product rule, the derivative of f times g is f prime g plus f g prime, then your triple product rule for the derivative of f times g times h is exactly what I just said. The derivative of one piece multiplied by the not derivative of the other pieces, and each piece's derivative has to come up one time. So I'm going to have f prime times the other two pieces plus, I would probably write it as g prime times f times h, but I'll write it as g prime times the other two pieces, f times h, plus h prime times the other two pieces, f times g. So each derivative gets to show up once, and it shows up multiplied by the other functions, not derivatives. And if you really wanted to, you could do the same thing for a quadruple product. And it would have four pieces, and each piece would be one derivative times the other three not derivatives. I'll write it out, even though I don't think I really need to. So if you have the derivative of f times g times h times j, it would be f prime times g times h times j plus f times g prime times h times j plus f times g times h prime times j plus f times g times h times j prime. So we could have done that for the previous problem. Be like, oh yeah, we can just say it's f prime times h times j plus f times h prime times j plus f times h times j prime. Do you need to memorize this? No. Is it useful sometimes? Yes. Okay. That's pretty much all there is to the product rule. You just have to remember that. So the thing I would emphasize is, remember that when you take the derivative of a product, you should always get a sum. It should be something plus something else. Because often that's the part that gets forgotten. People just kind of want to take both derivatives and smash them together by multiplying. Right, we have to take derivative times not derivative plus then the other not derivative times the other thing's derivative. So after the product rule, there's the quotient rule, which I think of as being very similar to the product rule. So if I want to take the derivative of f divided by g, I want you all to observe how the numerator of what I'm about to write looks almost exactly like the product of what I've written right up here. Almost exactly the same, except instead of f prime times g plus f times g prime, it's f prime times g minus f times g prime. So you have to be a little extra careful here. The order does matter. Here, the order doesn't matter. You could have done this as f g prime plus f prime g and would still be the same, because order of addition doesn't matter. 3 plus 5 equals 5 plus 3. Order of subtraction definitely matters. 5 minus 3 doesn't equal 3 minus 5. They're opposites. So just be careful. And then in the denominator, you get the square of g. So that's your quotient rule question. Totally, yeah. Order of multiplication doesn't matter. In fact, even though, so this is, I would say, this is the standard way of presenting this derivative, but I will tell you, in my head, these are the words I say. If I'm taking the derivative of the top function over the bottom function, I am always going to say it as the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So I actually write it out as g times f prime minus f times g prime all over g squared. But again, you can interchange order of multiplication to your heart's content. You just can't interchange the order of subtraction. That's the worry. So yeah, it's totally think you can think of it as f prime g minus g prime f, or if you're me, you can think of it as g f prime minus f g prime. Totally fine. Yeah, good question. Thank you for asking that. So then we can take derivatives of any sort of funky looking fraction. And things can get pretty gnarly pretty quick. By the way, just for those of you that came a little late, there are a few handouts there. And they are on Canvas as well with answers to some of them, solutions to some of them. So definitely, if you're looking for more practice, there's lots of good practice there. I highly recommend you grab one or get it off of Canvas and do the practice if you've run out of other things to practice. Well, yeah, so some of them, two of the handouts have answers, and the third one has solution. The difference being answers are just like, here's the derivative. Someone did all the work and simplified it, and there's your final answer. Whereas solutions are going to show you the steps to get to that final answer. That's whenever someone says answers versus solutions in math, that's what they mean. Answers the final product, solutions is showing you some of the steps. So let's say we want to find, say for our function f of x, which is, I don't know, x cubed plus 1 divided by, sure, cosine of x plus x squared. We want to find the derivative of that monstrosity. And you do not want to simplify unless you're asked to. Yes, later on we will need to simplify things because you're trying to solve some sort of thing. But at this point, we're just trying to show that we know how to take a derivative. So it's going to be the bottom cosine of x plus x squared times the derivative of the top, which is going to be 3x squared, minus, then we switch it up, it's going to be the top, x cubed plus 1, times the derivative of the bottom, which is going to be, let's say, the derivative of cosine of x is negative sine of x, plus the derivative of x squared is 2x. All that divided by the denominator squared. End of story, pretty much. Like, that's kind of all there is to it. And now that's nothing, but there's not that much more. I don't know. I'm trying to say something, but I don't really know what. There's not a lot more process to it. It's just kind of do the thing every time. Sometimes it gets more complicated, but in a very straightforward way, that's what we've got. So let's actually look at something that's a tiny bit more complicated. Yeah, actually, why don't I have you all try something first? Oh yeah, let's do this one. So why don't you all try taking for g of x equal to e to the x divided by sine of x, find the derivative using the quotient rule. For me, I'm always actually saying it the way in my head that I said it before. I'm really saying the bottom times the derivative of the top, and the derivative of e to the x is e to the x, minus the top times the derivative of the bottom, divided by the bottom squared. You don't have to say it that way. Like some people do, there's also like a kind of songy kind of thing, low d high minus high d low over low squared. That works too. Whatever works for you, as long as it works. There was something else here. Oh yeah, but things can get more complicated. For example, if my function looks like maybe say x cubed times cosine of x over x to the fifth plus e to the x. Sounds very violent over there. Now, in addition to having to use the quotient rule, we're also going to have to use the product rule when we have to take the derivative of the top. So here, our derivative, let's just write it down here, f prime of x is going to be the bottom, x to the fifth plus e to the x, times the derivative of the top, which you could either do right now or just write as x cubed cosine x prime, and then in the next step, actually find this derivative. I'm going to do it right now using the product rule. So we're going to have the derivative of the top, so it's going to be product rule, the derivative of the first thing, times leave alone the second thing. I'm going to be smart here. I'm going to look ahead. I know that when I do the flip side, it's going to be x cubed times the derivative of cosine, and the derivative of cosine is negative sine. So instead of writing plus x cubed times negative sine of x, I'm going to write minus x cubed times sine of x. So that I don't have to write plus x cubed times negative sine of x. Right, that's what I'm getting though, right? It's the x cubed times the derivative of cosine, which is negative sine. Okay, that's our bottom times our derivative of our top. Now we have to subtract and do our top, x cubed times cosine of x, times the derivative of the bottom, which is 5x to the fourth plus the derivative of e to the x is still e to the x. All of that divided by the denominator squared. And no, because there isn't one over here to factor out. So just so everyone's clear, we've got here, right? If this is your top and this is your bottom, then here we have, yeah, I don't want to do that. Sorry, it's terrible. There's the derivative of your top. Or sorry, that nope. Oh, wow, is that what I wrote there? Is that what that is? Is that the derivative of the top? Of course, that's not the derivative of the top. What is that actually? It's the bottom. Oh my God. Okay, that's the bottom. There's the derivative of your top. And then here's your top times the derivative of your bottom. All over your bottom squared. Cool. Yeah, we got enough time. Okay, so we won't get to the chain rule today, but we'll get to the chain rule on Thursday. But let's do one more thing. Let's talk about the derivatives of the rest of the trig functions, which you can certainly derive, but you definitely should just memorize. So let's start with tangent. So I want to find the derivative. Also, I want to point out, I do like to go back and forth between my derivative notations. Sometimes I'll say my function is this and the derivative is f prime. Other times I'll write d dx, meaning take the derivative with respect to x of whatever your function is. They're both totally valid. Everyone uses both of them all the time, so you should get used to seeing both of them. So the derivative of tangent, we're going to write as the derivative of sine of x divided by cosine of x. And then we're going to use the quotient rule. So it's going to be the bottom times the derivative of the top, derivative sine is cosine, minus the top times the derivative of the bottom, which is negative sine, all divided by sine, oh, sorry, cosine squared. Holy smokes, James, geez, it's terrible. That's awful. Apologies there, sorry. Okay, let's simplify this a little bit. This is equal to cosine squared x minus sine times minus sine is plus sine squared x, all divided by cosine squared x. But then we get to use a trig identity because it's well known that cosine squared x plus sine squared x is always equal to 1. But then 1 over cosine is equal to secant. So 1 over cosine squared of x is equal to secant squared of x. And there's kind of a really nice pattern with some of the trig derivatives. In my opinion, you kind of only need to memorize like 4 of them. I'll tell you what I mean after we've derived the other 3. So let's find the derivative of cotangent in very much the same sort of way. Interesting. Huh. Do I want to do it the same way? Let me think for a second. I'm gonna do this slightly different than I usually do, actually. So let me show you. I'm gonna show you a different way to do this, just because I think it's interesting and not unworthwhile. So cotangent, you could, but we're not going to. You could write cotangent as cosine over sine. Very typical way of writing. It's the reciprocal of tangent. But you could also write it as the reciprocal of tangent. And now we can use the quotient rule. It's going to be the bottom times the derivative of the top. What's the derivative of the top? 0. This is actually, I'm doing it this way so that you can see one where the top is a constant, so that the dot part's just going to be 0. Minus the top times the derivative of the bottom, which is secant squared x, as we just found out, all divided by tangent squared x. And although it is equal to negative secant squared over tangent squared, no one is ever going to write it like that. So let's see what happens when we simplify this. This is negative secant squared x over tangent squared x. If someone's ever asking you to simplify a trigonometric expression, it's usually in your best interest to write everything in terms of sines and cosines and try to figure out what's going on. So I'm going to write this is negative secant squared is really 1 over cosine squared, and tangent squared is really sine squared over cosine squared. And then if we flip and multiply, that's negative 1 over cosine squared x times cosine squared x over sine squared x. And the cosine squareds cancel, and you get negative 1 over sine squared x, which is then negative cosecant squared x. Or you could totally have done it the way we did tangent by doing it as cosine over sine. And if you did it that way, I'll just point out that if you do it as the derivative of cosine x over sine x, you get bottom times the derivative of the top, so you get sine x times negative sine x minus the top times the derivative of the bottom, which is negative cosine x times cosine x, all over sine squared. And look, it's exactly the same. Because negative sine squared minus cosine squared is the negative of this trig identity, which is going to be negative 1. So you also get negative 1 over sine squared x, which also leads you to cosecant squared x, negative cosecant squared x. Okay, we got 2 more, and we definitely have enough time. And then we will talk about the pattern, because I do think the pattern really makes it easier to memorize these. So let's do the derivative of secant. Yeah. So secant is 1 over cosine. So for all these other 4 trig functions, these other 4 quotient trig functions, we use the quotient rule. It's going to be at the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. Cosine x times 0 is just 0. So you get a negative 1 times a negative sine. So you get a positive sine of x over cosine squared of x. Again, nobody writes it this way. This is not, if someone said the derivative, if you got someone what the derivative of secant was, and they said sine of x divided by cosine squared of x, you'd say you're an insane person. Nobody says it that way, because everybody simplifies this as 1 over cosine x times sine x over cosine x, and then simplifies that as secant of x times tangent of x. So the derivative of secant of x is secant of x times tangent of x. And now I'm going to tell you what the pattern is going to be before we do this last one so you can see it. So looking back for just a moment. So looking at tangent, the derivative of tangent is secant squared of x. And then what I like to imagine doing is just kind of adding on the prefix co. So I'm going to put a co in front of the tangent and a co in front of the secant squared. And I'm going to say the derivative of co-tangent is co-secant squared with a minus sign. And it's going to work the same here. The derivative of secant is secant times tangent. The derivative of cosecant is cosecant times cotangent with a minus sign. And it's going to work. Let's check it out. But it totally works. I think it's great. So the derivative of cosecant of x is really the derivative of 1 over sine of x, which is really going to be quotient rule, bottom times the derivative of the top minus top times the derivative of the bottom, all of the bottom squared. And again, we're just going to rewrite this as, instead of negative cosine of x over sine squared of x, we're going to write it as negative 1 over sine of x times cosine of x over sine of x, which is really just negative cosecant of x times cotangent of x. So great. Those are all the trig derivatives. I had something here that I wanted to see. All right, one second. Papers everywhere. Where's the one I was looking for? All right, I want to make sure I say this thing the right way before I say it. Yeah, where'd you go? Sorry, I had a little list here. Now it's gone. I see it. Cool. So, a few observations. Here's what I'd recommend memorizing. Your functions and your derivatives. And they do go together in co-function pairs. So I think of sine and cosine going together. The derivative of sine is cosine. The derivative of cosine is negative sine. I think of tangent and cotangent going together. The derivative of tangent is secant squared of x. The derivative of cotangent is negative cosecant squared of x. And thirdly, secant and cosecant go together. The derivative of secant is secant times tangent. The derivative of cosecant is negative cosecant times cotangent. One thing I've noticed many times over the years is that the derivative of every co-function, cosine, cotangent, cosecant, is always negative, right? Those are the derivative of cosine is negative sine, derivative of cotangent is negative cosecant squared x, derivative of cosecant x is negative cosecant times cotangent. And then you have this nice pattern. Oh, and I'll say one more thing because a student showed me this. So this works for me. I think this is great. But one time a student showed me this, which I also thought was kind of cool. They drew this little thing that totally worked for them. They wrote like, yeah, they did this. The tangent, and then an arrow to the right, secant, and then an arrow to the left being secant. And they said to themselves, the derivative of tangent is secant times secant. Their secant is secant times tangent. And then they also did the same thing for cotangent, negative cosecant, and cosecant. Derivative of cotangent is negative cosecant times cosecant. Derivative of cosecant is negative cosecant times cotangent. It's not the best for me. If that works for you, cool, it works for you. So there's another way to try to remember them. You definitely should memorize these. I recommended when I had to memorize something for my own math class I was teaching one year that was really hard for me to memorize, I made it the lock screen on my phone. I saw it every time I looked at my phone, which is not infrequently, and I was like, oh yeah, there's that thing I should think about. Let me spend a second memorizing it. So definitely memorize this. It's not gonna go away. These derivatives are gonna be here for the rest of your math career. So memorize those, memorize the product rule, memorize the quotient rule, memorize the power rule. They're going to be your bread and butter for the next few weeks, so they're not going away. A few weeks is probably an underestimate, probably for the rest of your calculus career. So yeah, you still take derivatives in 17B, even though there's integrals. In 17C as well. So yeah. All right, I'll see you on Thursday, where we'll try to talk about the chain rule and the implicit, and then we'll also address any exam review you want to go over. Yeah, that's the plan for Thursday.